Okay, so we're going to talk about the MEMS cantilever applications overview. All right, so we're going to learn about where cantilevers are used in the world of MEMS, in the world of microsystems. Okay, the reason I've picked cantilevers is because they're used all over the place in microsystems devices. They use them in biomedical MEMS. They use them in radio frequency MEMS devices. They've used them in inertial sensors as well. So since it's such a broad impact and used in so many different places, that's why we want to talk about them as a separate topic. Okay, so by the end of this series of lectures, even this first lecture, you'll be able to define and talk about 4 different applications in MEMS where cantilevers are used. And then what are the advantages and limitations of using cantilevers compared to large cantilevers? Okay? So, the definition of a cantilever is that it's a suspended beam supported only at one end. Okay? And that's what you guys talked about before the lecture. Aircraft wings, balconies, freestanding radio towers, those are examples. The most familiar one, of course, is the diving board. They come in all kinds of sizes, and you can change the properties of how a cantilever vibrates, for example, by changing properties such as length and thickness, adding mass to it, using different materials. Micro cantilevers can get very, very small, in the hundreds of microns or smaller in length. Okay? Here's one application. This is from Nascatec, which is a company in Germany. They make micro cantilever systems to be used in atomic force microscopes. So you can see right at the tip of this image, you can see there's a cantilever on the end. Okay, so that's used in a probe device. Okay? We also use cantilevers as a transducer. So you can sense something with it, but you can also use it as an active device by applying a electrostatic force to it or a voltage. You can get a cantilever to move. Okay, needles are considered to be cantilevers. So in the medical industry, of course, you have the common needle that people use to stick you, right? But there are also micro needle arrays that are used in patches. So a lot of the patches people wear these days that deliver drugs to their system, the drugs are put on an array of micro cantilever needles. And they're so small you don't feel them. Feels like an adhesive, but they're really very small needles that break the skin and can get the drugs underneath the skin where it can be absorbed by the body. Okay, so they're used to detect physical, chemical, and biological systems or particles. And as we said, they can penetrate the tissue. And we can use them for transport mechanisms and sensors. And we can detect nano-sized particles on a surface. We can even detect individual molecules if we do it right. Okay? Okay, some of the areas where we're using MEMS devices that are cantilever-based include the biomedical apps, pH sensors, therapeutic devices. This is a famous one, the atomic force microscope. Read-write storage devices. One example is the IBM Millipede. There's another company, I think they're called Nano Storage, that uses cantilever arrays to read-write information onto a small mechanical surface. Environmental monitoring is another application. Of course, food production and safety is becoming a big issue these days. And RF switching. RF stands for radio frequency. Okay, so if you want to pass a very high frequency through a wire, through a switch, you can't do it through a transistor. Transistors are limited to about 3 to 4 gigahertz. So if you want to pass a high frequency signal on a wire, you have to use a mechanical switch. So you going back to the old days of using an actual mechanical switch. So how are they made? Well, this is one example. Okay, this is a silicon substrate. Okay, that's been etched out underneath a silicon nitride cantilever with gold on top of it. That's a typical structure for a micro cantilever. There's lots of ways to make these cantilevers. This is one such way. So we can use anisotropic etching. For example, the potassium hydroxide, which we talked about in the crystallography unit. Right? That certain type of etchant will follow the crystal planes. So you can etch underneath something that doesn't etch in potassium hydroxide, for example, gold and silicon nitride. So you can make these kind of structures. Okay? People have made cantilevers out of just about any material you can think of. And you want to choose the physical dimensions depending on your application. Okay, so some will be bigger, some will be smaller, depending on what you want to do with it. So needles and probes, you might want them to be stiffer than some other cantilevers. So you'll pick your material based on how stiff you want it to be. And you'll also pick the geometry you're going to design it as. Right? If you make it very long and skinny, you can imagine it's going to be more flexible. If you make it shorter and thick, it's going to be stiffer. So that's part of the design process, making sure that the stiffness is enough so that it's applicable to what you want to do with it. So sensors, for example, cantilever sensors tend to be very flexible. And switches have to be flexible so you can turn them on and off. But if you're making a needle array, you probably want them stiffer. You don't want them bending. You want them to penetrate. Okay? I'll show this video later. It's not working in the PowerPoint. So at the end of the lecture, I'll show the video. But MEMS cantilevers are made or fabricated. Fabricated is like made or manufactured using bulk micromachining or surface micromachining or a combination of the both of them. Okay, so in each process you get a solid structure. When you're done with it, you release the moving part, which in this case is the diving board or the cantilever. So you have to get rid of this material underneath, and you'll see that in the video. It explains that real well. So here we see the cantilever fabrication short animation. I decided to put this in after the lecture so you can see what's going on. The blue material represents silicon nitride that's been patterned and etched with a reactive ion etching process. This acts as a hard mask. So the gray area that shows outside of the blue and gold areas is crystalline silicon. Now we can etch crystalline silicon using potassium hydroxide, also known as KOH, and that will actually etch along the crystal planes. That's why you see the triangular formations underneath the masked areas. That is representing the 111 plane, which doesn't etch as fast as the 100 plane. The pink material is an etch stop material, which could also be silicon nitride, for example, and that keeps the etchant from continuing through the entire wafer. Now we can also do boron doping of the crystalline silicon, which greatly reduces the etching of potassium hydroxide. So that's another way to do an etch stop. So you can make one cantilever by itself, or you can easily make thousands of them in an array. So you can do different things with them. You can have different applications, or you could have an array of switches. Okay, let's say you have a cell phone application, and you need a different size antenna depending on what system you're trying to latch onto. Right? T-Mobile in the US might use a different frequency than they use in the United Kingdom. So you need different antenna lengths to do that effectively. You could use an array of switches that contact the antenna at different points, effectively having a different antenna length. So that's one application people are using for actuated cantilevers. Okay? The other application would be, let's say you wanted to coat each one of these with a different material and use it as a sensor array. Okay, and you'll learn about how that actually works in the other unit on how cantilevers work. Okay? So what are some of the characteristics of a MEMS cantilever? Well, you need to be able to measure something if you're going to use it as a sensor. And you can easily do that with a cantilever. You can measure the resonance frequency of it. There's different ways to do it. If you can measure how it vibrates and how fast it vibrates, you can use it as a sensor. And that's also part of the atomic force microscope cantilever. If you make the cantilever very small, you can also sense very small things. Makes it more sensitive. Cantilevers generally don't use a lot of power. So if you make a sensor out of it, it's not going to wear down your batteries, right? That's always a concern with any kind of application. And you can, like I said in the last slide, you can make a high density array. So you can put thousands of cantilevers in one product if you want to. It's like making a computer chip with thousands or billions of transistors. Okay? It's not hard to do. So here's a simple prototype device from the University of California at San Diego. Okay, this gentleman made 8 cantilevers. Okay, and he coated each one with palladium nickel films. Okay, and you use different materials depending on what you want to sense. And he has 2 reference cantilevers. Right, you need a reference to compare to, because every time you make a cantilever, it's going to have a slightly different vibrational mode. So you usually make a couple of reference ones to compare to, so you know when you sense something on the other ones. And you can get down to the nano with these. You can make them very, very small. So here's a schematic of how a cantilever works as a chemical sensor. So here is perhaps silicon nitride. You put a little bit of gold on top. Your probe coating is designed to detect what you're looking for. So the chemists will make different probe coatings depending on what you want to see or what you want to detect. The reason we put gold here is the chemists have gotten very good at sticking things to gold. Okay, you use sulfur. Sulfur sticks to gold. Sulfur is a nice material because you can build molecules on the end of sulfur. So they build various molecules. They have a sulfur end on it that sticks to the gold, and another end of the molecule that is designed as the probe. So if a target molecule comes by, it'll stick to it. Or you'll put an antibody on it. So if the virus that the antibody sticks to will stick to the coating. Okay? So you want to make this coating sticky to only specific things. Does that make sense? Okay. And the reason you put the gold down is because that's what the sulfur sticks to, but you can also control where you're going to put the coating. Otherwise, you might coat everything in there and nothing will work, right? It gets all fouled up. It's called biofouling of the sensor, if things stick to everything. So you have to be careful to design it so your probe coating only sticks to a certain part of your sensor, and then you can sense different things. So you might look for certain types of particles, or you may look for certain types of chemicals or analytes, right? And you do that by designing the coating accordingly. All right, so how do you measure things using a cantilever? Well, if you think about it, the cantilever can bend, right? Let's do a thought experiment, or a Gedanken experiment. That's another term for a thought experiment. If you have that probe coating on your cantilever, and it's designed in a way so that the chemical, when it gets absorbed into the coating, causes the coating to expand, what's going to happen to the cantilever? It'll deflect, it'll bend, right? So I'm going to pick up a meter stick, okay, and if you imagine a coating on it, on the top of the meter stick, and the coating wants to expand, right? It wants to be longer than the meter stick, so it's going to bend. Okay, so it's going to bend away from the coating. If the coating contracts, it's going to want to bend in the opposite way. It's going to want to pull the meter stick so that it bends in this fashion. Right? Does that make sense? So either it will bend up or it'll bend down, depending on if the coating's going to want to stretch or contract, expand or contract. There are materials where you take two different metals, right? Bimetallic structures. And when you heat them up, they bend. The old thermostats have a coil in it, right? Did you ever take one apart? If you heat it up, the coil either expands or contracts depending on how the metal is put together. Okay? So that's an example of that phenomena. In that case, heat is causing it to bend. But you can also create a coating that, if it absorbs something, it'll cause it to bend. Okay, so that's angular deflection. And so you can use a cantilever in static mode. It means it's not vibrating. You're just going to look at it whether or not it deflects. You can also put a piezo-resistive material inside the cantilever. There's ways to do that. Remember what a piezo-resistive material does? You add stress to it, changes the resistance of the material. So now I have an electrical method of measuring the stress in the cantilever. So now if my coating, my probe coating, absorbs a material and it bends, it's going to change the resistance in the embedded piezo-resistive material, and you can detect whether or not it's bending or under stress. It's another way of measuring what's going on. You can reflect light off of the cantilever. The reflection angle will change if the cantilever bends. Think about it, right? I'm going to use the meter stick again. If I bounce a laser beam off the end of the meter stick, it's going to hit a certain part of the ceiling, right? What happens if I bend it? It's going to change, right? So all I need is a position-sensitive detector that detects the change in the reflected light, and we can understand how much that cantilever deflected. So in the case of a coating, if you have more stuff absorbing into it or less stuff absorbing into it, it'll deflect at different angles, and you can measure that. And another way to measure what's going on is, we talked a little bit about this before the lecture. If you add mass to a diving board, if a larger person's on the diving board, it'll vibrate slower than if a smaller person is on the diving board. So if you can look at the natural frequency or the vibrational frequency of the cantilever, you can tell if something has been added to it or not. It'll vibrate slower if it's absorbed something. Okay, so the trick is in the coating, and then how you're going to determine what's stuck to the coating, either by looking at how much it bends or how much it changes its vibrational mode. Okay. So cantilevers are fabricated as a single device or several devices arranged in an array. Okay, in this case, it's a needle array, but you could make an array of cantilevers, as we discussed. A chemical sensor array is a type of measurement system. So you make an array of cantilevers or other sensors. They're designing other ones. But each sensor can be coated with a different probe coating. So you can make an artificial nose, right? Each cantilever picks up on some other or different chemical or different virus or antibodies in the blood. And you can create sensors to detect a lot of different things. Okay, but there are artificial noses. There's a spin-off company in Albuquerque that has used this technique to create a device that can sense an array of different materials. It's called the hound dog, right? They're trying to be like a basset hound that can detect a lot of different things. We still use dogs at the airports, right, to detect explosives, different kinds of foods that we don't want to be imported into the country. And drugs, of course, too, right? Dogs are very good at that. But they're making artificial noses that are getting close to being as good as a dog. And those are nice because you can put them up in the airport, run them 24 hours a day, 7 days a week. They don't get tired. You know, you can only run a dog a couple hours a day, and then they don't smell anything anymore. Yeah?
You think they're trying to mimic what happened in the dog's nose? Is the same thing going on in general that it's going on here?
In general, yeah. I'm not real keen on exactly how a nose works, but it's an array of sensors. And when a specific sensor gets excited, it sends a signal on that nerve path, and then the brain interprets that. And if there's a combination of excitations for different molecules, the brain puts it together and says, oh, that's a rose, or that's cheap perfume, or that's a good bottle of wine, right? Or a Lemberger cheese, exactly. You know, the hope is that you can activate the array of cantilevers with whatever you're looking for. So you have a base product, and you just put different coatings on it. Okay? So that's where they're trying to go with these. And this is a cartoon of kind of how it could work. You have different coatings here with different materials on them. And you can discriminate the different materials because the target materials will land or will only stick to the specific probe coatings. So in this case, you know, the first cantilever has a probe coating that likes these green target materials, these green spheres. The next one, only the purple ones stick to that. The purple ones don't stick to any of the other ones. And you get the idea. So you can make an array of cantilevers very small, coat them with different materials. You can use inkjet print technology to do the coatings, right? You can specify which coating goes where, and create these chemical sensor arrays. And there's a full-blown learning module on that you'll see later on. They've made gas leak detectors, detection for different types of chemicals in liquid, biosensors. Okay, looking for specific antibodies or viruses, proteins, enzymes, DNA strands. Okay, you can create coatings that look for specific proteins. Of course, pH, if you have a different pH, the coating will expand or contract depending on the pH of the solution. So when you have sensors or cantilevers of that sort, you're looking at how much the cantilever bends. And you can look for biomedical markers as well. Okay? So what are the advantages? Well, it's small. Why is that good? It's cheaper to make, less materials. You can throw it away when you're done. Don't have to sterilize it. Just get rid of it. It's cheaper. Okay, you can look at a lot of things with one device. Has very good sensitivity because it's small, and selectivity depending on the coatings. It can work in air, vacuum, or liquid. Not sure how good it would do in a vacuum if there's nothing to sense. I don't know if we wanted to put that in there. It has a wide dynamic range, and again, little power is used. They've tried to use microcantilevers as a transport device, kind of like the cilia on single-cell organisms. Like protozoa, if you look at them in the microscope, they swim around in the water and they have all these little hairs that stick out of them that move, like oars. Well, those are cantilevers that are actuated, right? So people are trying to use cantilevers to actually move things around. And as we mentioned, we use them in atomic force microscopes. So we actually activate the atomic force microscope cantilever to move up and down as it goes across the surface and keeps a constant distance above the surface. Okay? So some examples of a transport device would be the atomic force microscope. Here we have a cantilever with a probe tip on the end. It's usually very, very sharp. You can make these probe tips out of crystalline silicon. So you use that crystalline feature and etch a very sharp point, and at the end of the point is a single silicon atom. That's the probe. So you can get very high resolution. To see which way the cantilever itself moves when it goes up and down as the surface is moved underneath. As this moves up and down, the reflected laser beam will move. And if you have a position-sensitive detector, you know exactly how far up or down that cantilever is moved. And you can translate the motion of the reflected laser beam to what's happening at the tip. Okay? You can get an array of these cantilevers and actually make a device that can read something that resembles Braille, but on a nanoscale. Right? You have these little divots on a polymer film, and you can read the divots, and you can make the divots with the cantilever tip itself. Okay, so that's a read-write storage device. Yeah, going back to the Feynman paper, as long as you can see something or read something, then you know what you're doing to that material or device. So if you can measure motion or measure disturbances or topology of materials, once you can measure it, then you can also come up with ways of changing it, because now you can measure it. So the atomic force microscope can measure small variations in the surface of a material down to the size of an atom. So why not be able to write down to that size? This is about a nanometer across, this divot, which is probably equal to, what, 10 angstroms, which is maybe a few atoms across in space. So they can deform this material on a very small scale and read it on a very small scale. The densities they've gotten up to is about a terabyte per square inch. Terabit per square inch. That's a lot. You know, that's a lot of bits you can put on a one inch square surface. Okay? So that's a really cool device. I invite you to go look at it. I misspoke. The probe tip's about 10 nanometers across. So that'd be about 100 angstroms, which is about 100 hydrogen atoms worth of material. That's still pretty small. Okay, so we've gone full circle. We've gone from writing and making divots in clay, you know, 5,000 years ago, to putting it on magnetic material and then optical material. Now we're going back to mechanical again, storage. These can't compete with the with your flash drives in terms of cost, but special applications, this would be really good, maybe in space, right, where electrical systems can be damaged by cosmic rays. Mechanical systems have a harder time of getting damaged. Okay? And if you look at it closely, you can see this is an array of cantilevers, right? And they're kind of, they have two structures on them. So you can see it here. You can pass a current through this cantilever, and where it's real thin, it'll heat up. And when you heat it up, you can form the divot in the polymer. If it's a hot tip and it falls into a divot, it'll cool. So if something's heated, it has a different resistance. If something's cooler, the resistance changes. So that's how they use it to detect whether or not a divot's there. Okay? So this is a picture here of a 64 by 64 array of cantilevers. So they do multiplexing. They have 4,000 cantilevers all being actuated at the same time. And each cantilever can write on a 100 by 100 micron space. Okay, you can use them as switches. If you want to pass a signal, for example, a 50 gigahertz signal down a wire, you can't use a transistor to do that. They don't resonate that high. But you can use a mechanical switch to send the signal down the line. Okay, and since you're using electrostatic power, which is just applying a voltage to something, it doesn't use current. Okay, think about that. If I apply a voltage to a capacitor, there's very little current flow, only when I set up that voltage, and after that there's no current flow. So that means there's no power used, or very little power. Right? So people like electrostatic actuation because it uses little power. Here's a cartoon of how it works, a schematic. I want to make a connection from here to here. Okay, maybe these are two wires coming in next to each other. You only see one of them in this view. You want to connect the two wires with a contact up here. You pull down this switch by applying a voltage on this actuation pad. Pulls the cantilever down, it makes contact with the two wires. And now we can transmit that radio frequency down that wire. We let the voltage go, the spring action of the cantilever pulls it back up, and you turn it off. Okay, it's a simple switch. Here's our microneedle array for doing transdermal drug delivery systems. We can look at very small amounts of material if we use very small sensors. Okay. Here's an array for doing research on the brain. This array here is, this picture is actually a scanning electron microscope picture of a probe array that's on the end of this small device here. Okay. So each one of these shanks is about 30 microns wide and 1.2 millimeters long. So it's 8 by 16 array. And that's so you can both detect and actuate specific parts of the brain in a very small region. And then the cochlear implants, another example. They do use cantilever type structures within this device to actuate things. Okay? So this is one of the important emerging technologies. A lot of people have these implants already. And there's a good website for folks to learn how to get a cochlear implant and how it works and what types of deafness it can help with. Okay? All right, so lots of applications. Right? One of the main applications is what? What do you think? Sensors. Yeah, that's a big one. Another application. Switches. Okay, good. Deformable mirror? Yeah, it does. You pull down the switch, the cantilever switch with an electrostatic force or a voltage. You pull down the deformable mirror with an electrostatic voltage as well. It's the same principle. Except in the case of the deformable mirror, you usually have an array of voltages, and they're each accessed separately. But you could probably create a cantilever array and put maybe a membrane on top of it, and then pull down each individual cantilever differently to get a shape distortion in the membrane. You could do a hybrid of that, or make a pump. They've been making transport devices where you can resonate not just the individual cantilever, but if you have an array of cantilevers hooked up to the same structure, base structure, you can get waves going down the cantilevers themselves. So each cantilever will go up and down in a wave pattern from one side to the other side of the array. And you can use it to transport things. You can use it for all sorts of other stuff. So there's, the sky's the limit to your imagination. Once you get the basic cantilever working, you can do different things with it. It's like gears, right? Once you develop a gear, you can do lots of things with it. Okay, so what are some other applications maybe that wasn't discussed in the presentation? I mean, you mentioned the deformable mirror. That's kind of along the lines. Can you guys think of anything? Energy harvesting. How would that work?
Cantilever, piezoelectric material. When it's moved down, it induces a voltage. And it works off of vibrations more structure.
Okay, so you could have an environmental factor that causes the cantilever to change shape, either an outside force, right, or another kind of mechanism, and then that induces a voltage in the piezoresistive material within the cantilever, creating a voltage. And then if you turn that on and off, or you find a way to do it cycling it, you can actually store energy in a battery or cause it to move. That's really good. Okay, so you put your energy harvesting cantilever based device inside of a bridge, and as cars travel over it, the bridge will always vibrate. So now you have a power source for your micro pressure sensors or whatever that you want to power. That's really good. That's a really good application. Yeah, there might be a way to use a cantilever to produce an RF signal. I can't think of it right now, but maybe like the resonant gate transistor device, that's using a cantilever to produce a signal of a certain frequency. So yeah, you can do that. One thing I read about along the lines of the energy harvesting thing is if you have a radioactive source, right? and you have high energy particles come off of it, you can create a charge difference. So you can create charges in a system. So now you're charging your cantilever, it'll get attracted to another oppositely charged or grounded pad, and you can get it to move, and then once it touches, it shorts out, right? Discharges, and the cantilever moves back to its original position, and the radioactive source starts to charge it up again. So they're thinking about that for space applications, because radioactive sources last a long time, right? 10,000 years. So you could actually power a sensor, theoretically, for a very, very long time, using the combination of a nuclear or radiation source and an electrostatic motor, in a sense. So there's lots of cool stuff. Yeah, Sandia's worked on energy sources based on that, and they've gotten cantilevers to move like that. But that's still on the frontier. I don't think they have any applications yet. I'm sure they're thinking about, well, okay, how do we power our electronics within a nuclear bomb, right? It has a radiation source, so why not use it for something? Yeah, well, weapons applications has driven technology for millions of years, right? We wanted to build a better spear to get that mammoth. And all right, so how does application determine the stiffness of the cantilever? If you want it stiffer and less stiff, how does that drive it? Or if you have an application in mind, why would you want to change the stiffness? Sensitivity, in the case of the energy harvesting, if it's too stiff, it may not flex enough to produce that energy. If it's too flimsy, it may get stuck on something. Right, if it's stiffer, you're going to have to add more mass to it to see a difference. So you might have to adjust the stiffness. And there's different ways to do that. You might also want to change the stiffness to adjust the frequency it runs at, because your electronics off the shelf runs at a certain frequency, right? So if you make it too stiff, then now you're going to have to build new electronics to run that sensor. So you have to think about, okay, what's this sensor going to hook into? All right, so as we've stated, cantilevers are used in lots of different applications. The application itself determines, what shape or size, length, width the cantilever should be designed at, what material it should be made out of. The cantilever is the cornerstone component in a wide variety of MEMS devices and microchemical sensor arrays, atomic force microscopes, microswitches, neural probes, and whatever else you can think of. I mean, there's so much. So that's why I get hung up on cantilevers. Okay, so any questions?
So, like say on the energy harvesting part, so you have this real small device that has a cantilever that reduces the voltage and makes small amount of voltage. Instead of getting millions of those and putting them on a big device, why can't you make one big cantilever and do the same thing? Is there a reason that it works better as a small device than a big device, or is it just because it covers more area more effectively?
Well, that's a really interesting question. So make an energy harvesting device that's big, based on the same thing as a cantilever. It might get too stiff the bigger you go. And the frequency it resonates gets slower the bigger you go.
Well, you'd be trying to find something producing a large frequency, which not very many things to do in the macro world, right? There's a lot of tiny, smaller frequencies in the micro world going on.
Well, you can run at a higher frequency the smaller you go. So let's say you wanted 60 cycles per second. right? You'd have to design the cantilever to run at that. And you can, a macro-style device. But you'd need, in the case of, say, the radiation source, you'd need a lot of radiation to create that charge, to make it move, because it's so big. Now, you'd create more current when you discharge, too. I wouldn't want to be standing close to that device, though, if it has that much radiation. You could use, in energy harvesting, you can use temperature variation. And they've come up with devices to do that. Because at night it gets cold and at day it gets hot. You know, if you create the right array of devices, you can harvest power from that temperature change.
Anything you put them on, you know, by doing that would expand and contract, you can take advantage of that.
Yeah, expansion and contraction, absolutely. Or you can use an inertial system. You know, like there's watches you can buy that are self-winding. You know, you just wear them, and since you're moving all day, the little pendulum inside will wind up that spring. They make devices like that on the MEMS scale to store mechanical energy. But you could also have that mass moving inside of a coil of wire, like a Faraday flashlight, if you've ever seen those, right? You shake them back and forth, and the magnet goes in the coil and causes an induction in the current and charges a battery. And then you run your LEDs off of it.
You can do induction on a micro scale.
Yeah, you can do an induction on the microscale. It's a little harder because you need different materials. And it's hard to put those materials together on that scale. Right? There's a switch called the pinch hitter where they used a coil of very thin wire and made a micro switch. The problem was that a graduate student had to take very small grippers and coil the wire around a structure that was microns in size. So it's not something you could do every day. You could probably devise a robot that can do that kind of work, but you're only going to make one piece at a time. It's okay for space exploration if you have like 5 of these you have to make for some, you know, probe that goes into space. You can spend a lot of time and money to make 5 devices. But if you want to put them in cell phones, you know, they got to be really cheap, right? And you got to be able to make millions of them quickly. So you have to think about, well, how am I going to put this together? You can make a one-off device, show that it works. But how are you going to build it and make thousands or millions of them? So whenever you have an idea, you got to think about designing for manufacturing. Okay. Any other questions? Okay. We'll take a break. We still got 20 minutes. We're going to play with some cantilevers. Just get you prepped for the next one.